All right. Welcome back. Everybody on Zoom and in the classroom. So before we introduce the speaker or start the lecture, I want to discuss one question I had about the quiz from last week. I see correct. Okay. So I'll share my screen quickly so you can see what I'm talking about. So there was one question about this part of the quiz. So this question about the system and a functional in binary fashion. So either x performance was 1 or x performance was 0. That's speaking. Okay, so and you say I'm hard to hear. Is it better now? For the people on Zoom? Okay, thanks. So yeah, so this question. So here you have to imagine a kind of a rectangular resilience triangle. So you have more resilience rectangle. So the performance is 1 until the disruption is putting the system from full performance to no performance. So it drops to 0 instantly, remains at 0 for a while, and recovery is also instantaneous. So the performance goes from 0 to 1. So here, the question is, why was time to recovery the only relevant measure of resilience here? So here, for example, we wouldn't say time to strain because strain is instantaneous. It goes from performance from 1 to 0 instantly. So there's not a progressive degradation of performance. I don't know if it was one of you who was a question. No, okay, so maybe someone on Zoom. Why degree of return? Well, because performance goes from 0 to 1. It's really binary, so there's no way performance to go to less than 1 or more than 1 afterwards. And it's also not maximum performance loss because here, because of this binary character of the performance, the loss is either 1 or 2. So you either lose complete performance or you don't lose performance. So maximum performance loss doesn't really say anything because there's only 2 possible states of the system. So time to recovery is the only relevant option because it just tells you basically how long that is lost performance. So how long you're going to stay at performance 0. Because the degradation, which is instantaneous, and the recovery, which is also instantaneous. So yeah, so that was, I forgot who student asked that question, but I hope it's clear now why this was the relevant answer. Okay, let me just quickly look at the chat. Okay, better. Fine, so that is it. So I'll stop sharing my screen. Up. Okay. Share. Okay. So thanks, Alberto, for your patience. So now let's introduce our speaker today. Dr. Alberto Costa is a senior researcher at the Future System at Singapore, and he's working on topics all around complex systems, on optimization, on field application. I think Alberto, you're involved in a project on energy resilience of high-density urban systems. So that's, I guess, you can apply areas where you use the management complex systems. So today we discuss exactly this. So what is the role of robust optimization, optimization in general, in resilience? So that's all. Thanks for being here, and we look forward to your lecture.
Thank you, Helen. So let me share my screen and see if everything works.
Yeah, all good.
Can you see?
Yes.
Can you hear?
Yes.
Then we can go. Okay, so thank you again. This lecture and the next lecture will be around the topic of resilience, of course, but we are looking at it from the lens of optimization. So you start already, I guess, in the previous lecture to see the basic concept of resilience, and then what you are going to learn in these 2 lectures may be a little different. But it's very useful, and you will see, especially in the second lecture, there will be some kind of activities that will be quite interesting. This is the outline of the presentation today. So we have, of course, the introduction, the basic of mathematical programming, that is the kind of optimization we are dealing with in this course. Then the use of EMPOL What is Ample? Ample is the software that we will be using to solve optimization problems, because in this course, we are not just learning some of the basic theory, but also learning how to solve in practice optimization problems. That is a quite useful skill to have. And then we look at the max flow problem. That will be the main problem we are going to use in the second lecture. So as you know, we have for this optimization part of the course 2 lectures, one this morning, one next morning. You should have already installed Ample and Cplex, or rather you should do it before the next lecture. That will be more interactive. As I said, Ample is the software we will be using for solving the problem, for actually modeling optimization problems, and Cplex is the software that we use to solve them. If you have any issue with this, just send me an email, but you will see also at the end of these slides, there is the link where you can download the demo version of Ample. That is, it should be coming with the software already there. The demo version is enough because we don't need to solve huge problems where you need a full license. Objectives of this course, well, we want to learn what is mathematical programming, and we will be focusing on linear and integer programming. This will be clearer later, but optimization is very wide. So in this course, we are looking at linear and integer programming only. Then we will be learning how to model using Ample and how to solve optimization problems using Cplex. We will be learning later the concept of worst case scenario and robust optimization, because the way we are looking at resilience here is how to optimize against the worst case scenario out of a possible set of disruption scenarios that can happen. And then we want to apply this idea to the max flow problem that I mentioned earlier. So let's start with mathematical programming. What is mathematical programming? Mathematical programming is a branch of optimization where the focus is to find the best solution for a given optimization problem. Now, the best solution means that we have a set of possible solutions that we can choose from. And this is called feasible set. So you can imagine you have a set of solutions that are feasible, and then out of all of them, you want to find the best one. Okay. The feasible solutions are determined by constraints. So the constraints are the, if you want to look at them in the mathematical sense, they are inequalities or equalities that will tell you what is feasible, what is not. How to identify the best solution? We have a performance measure that in optimization is called objective function. And this is the one telling us the quality of each solution. And a solution is what? Is basically the value of some variables. So this is the abstract way to characterize mathematical programming. Later it will be even more clear. But again, I want to stress that the main components here are set of constraints that will characterize feasible solution, the variables of the problem, and the objective function that is telling you what is the best solution. Some example of these kind of problems, for example, is when you're driving, you want to go from point A to point B, and maybe you are in your car and use the navigator, and they tell you the shortest path. Well, the shortest path is an optimization problem. Out of all the possible paths that bring you from A to B, you want to find the shortest one. So in this case, the objective function, the performance measure, is the length of the paths that you want to minimize. There are others, for example, you can find application really in every domain, in architecture, in civil engineering. Here you have another example that I was working on this problem earlier. What is the best building design for maximizing energy efficiency? Or you can have application in finance, right? You probably know the portfolio optimization. And of course, we have the max flow that we will be describing later. So what is the procedure we should follow when we are addressing mathematical programming problems? And the first step that is often overlooked and yet is probably the most important is to formalize the real world problem. because often we are dealing with a problem that is described in words, or maybe someone is telling us the problem they have to solve and they come from another domain. So it's very important to understand the problem, to really have the picture clear in your mind. And only at that point you can create, and this is the second point, an abstract mathematical model to describe the problem. So this is the step 2, is where you are defining all your constraints and your parameters, the objective function, the variables, and so on. And of course, this is an abstract model. I want to stress this, because many times we cannot really describe one-to-one the real world problem. We need to make some assumption. We need to have a model that is maybe simplified, and this is important later. Then when we have this model, we give this model that we create with Ample, for example, the language I mentioned earlier, we give this as input to a solver. Cplex is the one I mentioned earlier again. And this solver is just a software that will take as input the model and the data and will give us as output the optimal solution. So we don't really focus here on how to find the optimal solution. We assume there is a software written by very smart people that will just tell us, hey, if this is the model, this is the optimal solution. Here we focus on how to create the models. And when you have the solution, then we need to interpret the solution. Why? Because again, in point 2, we have an abstract model. So we get a solution from our abstract model, and then we need to see if this makes sense when we apply that in the real world problem. Because maybe we had some simplification or some assumption, we need to do sometimes a kind of adjustment of the solution to make it relevant for the real world problem we are studying. In this course, as I wrote here, we focus on point 2 and 3. So how to create the models and how to solve the problem. Even though, again, the focus of this course is on the modeling, not on the solving. Right? We always assume we have a software that can take the model as input and give us the solution. So we don't really focus on the solution procedure. That is good news sometimes, because we don't need to care about all the details or the algorithms that are required to find the solution. Now, as I said, but I think it's worth repeating it, to create the model, we use a language that is called Ample. That means a mathematical programming language, okay? And it's not the only one. There are other alternatives. One is GAMS. There are also packages for Python. One of them is Pyomo. The reason why I don't want to use Python is because Ample focus only on the modeling. If you want to use Python, you also need to focus on the variables, and there is the Python. You need to be able to use Python, and this is a package. But Ample is just focusing on writing mathematical programming models. So I think for a course where we want to focus on modeling, this is a better choice. But if later you want to develop something, Pyomo is open source, so it's completely free. To solve the problem, we have solvers. In this case, we use Cplex, that is the state-of-the-art for linear and integer problems. That is our main focus. But then, depending on the type of model we create, we may use different solvers. So you may have nonlinear problems, you may have other stuff. And then I list here a few other examples of software that you may use to solve your problems. So this is something that I already mentioned. We focus on modeling, and the reason why we focus on modeling is that often is overlooked. And yet you can have two models describing the same optimization problem and use the same solver to solve them, and the resolution time can be very, very different. So writing good models and efficient model can have a huge impact on the time you need to find the solution of your problem. This may be scary for some, but is not so difficult to understand once we have gone through this slide. Because what this is telling you is basically that the structure of a mathematical programming problem is that we want to minimize or maximize an objective function is what I called earlier the performance measure. Shortest path, for example, when you want to drive from A to B, the function f will be the length of the path. Then you have st. St means subject to, and this is introducing the constraint of the problem. So the constraints I put here G and H because they can have different, like they can be inequalities, they can be equalities, okay? And then usually you have a constraint on the variables. Here variables are X, and they can be greater than or equal to 0, less than or equal to 0. They can have also signs, so is usually you have also a constraint on the variables. If you don't see anything by default, they are assumed to be non-negative, but they can have also other requirements. Something I want to highlight here, in optimization, usually you don't have strict inequalities. So you will never see, I don't know, X less than 0. You may see less than or equal to 0. Why? Because if you have to solve this with a computer, if I tell you, for example, maximize X subject to X less than or equal to 5, then you say, okay, the optimal solution is X equal to 5. But if I tell you maximize X subject to X strictly less than 5, then what is the solution? It will be 4.9999 and so on. And this will be a problem for the numerical precision of the calculator. So in optimization, remember, when you model a problem, usually you see strict, non-strict inequalities. If you have to enforce a strict inequality, you will put a tolerance. So you may write X less than or equal to 5 minus epsilon, right? But you don't see directly the strict sign, the greater than or less than without equal. So the problem described this way is I want to minimize the function f of x. Okay, this is the objective, and I want to find the x respecting these constraints, g of x less than or equal to 0, h of x equal to 0, and x greater than or equal to 0. Out of all the possible values of x respecting these constraints, what is the one minimizing f of x? This is what the mathematical model is telling you. Okay? If you have any question, just put in the chat, I can answer. But this is basically the main idea. Again, is the mathematical notation, if it's the first time you see it, may be confusing, but the main concept is not so hard. Constraint define the set of possible choices, the variables, the value of the variables that we can choose, and out of all the possible valid choices, we want the one minimizing, in this case, the function f. As I said earlier, in this course, we focus on linear and integer programming. So what did I mean by that? If you look at this is a very generic model. We didn't say anything about f, g, h. We don't know which kind of functions they are. If all these functions are linear, then this is called a linear programming problem. And it's usually the easiest way to solve, the easiest type of problem to solve. Then you may have integer problems. Integer is when still you have the function linear, but some of the variables may be integer. So for example, x, instead of being any number greater than or equal to 0, it may be any integer number greater than or equal to 0. So this small difference makes the problems harder to solve. Okay, harder to solve means you need more time to find a solution usually. But again, in this course, we don't focus on how to solve. Just for you to know that integers are usually harder to solve. Then if some of the functions like g, f, or h are nonlinear, you get nonlinear programming problem. And it can be even harder if you have nonlinear and integer. So this is called MINLP, mixed integer nonlinear problem, and is usually one of the hardest class of problems to solve. There are also other categories like convex, non-convex, stochastic, black box, robust. We don't really touch on that. We will say something about robust in the next lecture, but for now, we are looking at linear and mixed integer linear. Mixed means that you may have some variables integer, some no. Okay, so again, we are looking at these first two classes of problems. Now, the solvers, as I say, depends on the kind of problem you have. Of course, we can use AMPL or other languages to create the model, but then to solve the problem, if you have a linear problem, you may use a solver. If you have a non-linear problem, the same solver may not be a good choice. So in this case, we use Cplex because this is the state of the art for linear and mixed integer linear problems. That is the focus of this course. Let's look now at linear problems, because this formulation is very generic, is good to describe all these classes, but linear problems can be written like that. So we minimize or maximize is the same actually, a function C transpose X. C transpose X means you have a vector, so Cx are vectors, A is a matrix, and B is another vector. So this is the way we write that, is a linear function, and then we have a set of linear inequalities or equalities. If you see equal to or greater than or equal to, is fine. Like, is that the standard way to write the problem is with equality, but they are equivalent in reality. If you have a mixed integer linear problem, is basically the same, only that some of the variables you see here are integer. So what I did, I say every variable x is greater than or equal to 0, but there is a subset I call xi of these variables that are also integer. So the only difference is that the variables you see here is exactly the same model, only that some of the variables are integer. And modeling wise, that's all. That's the main difference if you create a model between a linear and mixed integer linear problem. Let's see how we can write these kind of models using MPOL. That is the software that we use in this course. MPOL, as I say, means a mathematical programming language, and it's very good because the way you create models in MPOL is very close to the way you would wrote it on the paper. You will see later what I mean. There are many ways to simplify your life with MPOL because they have a lot of constructs for defining sets, parameters, variable, objective. Everything we need in MPOL can be written very easily and very efficiently. They have, you will see later, the sum over set is one very powerful feature. And many solvers, not only Cplex, but also the others that I list, they work with MPOL. So what does it mean? It means that if I want to change the solver, I just need to change one line in MPOL and say, use this software instead of that software, and that's all. Because if the solver is compatible with MPOL, we don't really need to rewrite everything in a different way. The model is always the same. We just need to define that we are using a different solvers, and that's all. There is a resource here, the MPOL manual, that you can check if you are interested. But I mean, later I will share the slide with you, so you will see all the links inside. What are the basics of MPOL? How can we create a minimum running model? We need three things. We need a mod file. The mod file is the file including what I described later, so earlier, sorry. So the objective function, the set of constraints, and the variable. There is also a data file that is optional because you can write the data inside the mod file directly, or you can separate that is suggested to separate that into a data file. Why is it a better way to create a model? Because if I need to change the data, I just need to change this file. The model file remains the same. And then we have a RAM file. The RAM file is just a file to tell MPOL what is the model, where are the data, and then which kind of solver we want to use, for example, Cplex, and then the output that we want to show. This is the beginning of the syntax of MPOL. I will go through some of the main components, and then we will see later an example, a full example, so you will see how this is used. Now, the first thing is how to declare variables. You see, it's very simple here. We just use the keyword var, var means variable, followed by the name of the variable like x1, and we can also directly define the bounds. So the first line here means that we are defining a variable called x1, and this variable is non-negative. Okay. We can declare parameters. What are parameters? Parameters are the number, the data. So for example, here I'm declaring a parameter called a, and the keyword is param, and I can also say that the default value is 3. These values can be specified in the data file, as I said, but you can also write something like that in the model. So here we define a number, a parameter, with value 3. The main difference between variable and parameter, and this seems obvious, but when you start with the first models, it may be confusing, is that the value of the parameter is known before you solve the problem. The value of the variable is known only after you solve the problem. So if sometimes you are confused between parameter and variable, the easy way to know it is, do I know the value before solving the problem? If so, is a parameter, otherwise is a variable. Objective function, there are two things here. First thing is we need to say if it's a minimize or maximize. So in this case, we write minimize if we want to minimize. If we wanted to maximize, well, you just write maximize. Then you put a name to the function. In this case, I put fun, but it can be any name if it's not one of the keywords. So you can call it whatever you want. And then after this, you write the expression. So for example, here I'm saying that the function I want to minimize is called fun and is defined like that. A times x1 minus 2 times x2. x1 and x2 are variables that we defined earlier, and the parameter a is 3. So this reads minimize 3x1 minus 2x2. Then we have the constraints, and the way to define constraints is to use the keyword subject to. Then you put a name. It can be any name. Here I put as an example const, but it can be C1, C2. It can really be anything you want. And then similarly to the objective function, you define the expression. So in this case, the constraint we want to satisfy is x1 plus x2 equal to 4. Is it okay so far? Okay, so I don't see the chat here. Okay, nothing in the chat. Oh, we have a question. Okay. Then another thing I want to mention here, I say that the parameter a can take the default value 3. This is the way we define data inside the model. But we can also have in the data file that you will see later, something like that, where we say that the parameter a is, we assign value 3. This is the syntax, this is the way we do that in the data file. So it means that later we want to change this value in another data file, we can overwrite what we define here as default with this expression in the data file. But you will see this later. Then finally, the run file. As I said, in the run file, we need to do a few things. We need to tell Ample what is the model. So imagine the mod file, this one, with all these, the variables, parameter, the objective, and constraint. We call it example.mod. So we tell Ample, look, the model is example.mod. Data file, in this case, there is no data. Then we have to tell Ample which solver we want to use. In this case, we use Cplex. Then we tell Ample that we want to solve the problem. And then we tell Ample to show the value of the variables, in this case, x1 and x2. So the summary is this. Each variable must be defined with a var statement. The objective function is defined in a statement starting with minimize or maximize, and then you put the name of the function that is what you want. Constraint start with subject to. So these are the keywords: var, param, subject to, minimize, just a few keywords to memorize. Something else you see here that I wrote, for example, 2 star x2. So in MPOL, when you have a product, you cannot just omit the multiplication sign. You cannot write 2x2. There will be a syntax error. You have to remember to use this operator to specify multiplication. When we have relation like greater than or equal to, this is the way to write it. So you write the greater and then you write the equal. And display is the keyword that we use inside the RAM file to show the values of the variables. Let's do now the example that we described earlier. Let's create the full MPOL file. So the first thing, as I said, is to create the model, right? And this is the theoretical model that we have seen, the linear programming model, if you remember, minimize C transpose X subject to constraint and so on. Our model, the one that we just described, will be something like that. We want to minimize 3x1 minus 2x2. Remember, 3 was the parameter A, and the constraint of our model was x1 plus x2 equal to 4. And the two variables are greater than or equal to 0. So imagine that we want to write in MPOL this guy here. What can we do now? Well, if you compare this with the theoretical model on the top here, you will realize that a few things. The parameter C is the vector 3 minus 2, because C transpose X means the vector C multiplied by the vector x1, x2. So if C is this and the X is x1, x2, C transpose X is exactly this expression. And in this case, we don't really have, we just have a vector, like we don't have a matrix because like we have only one constraint. So if you want, you can write it like this: A is 1, 1, and B is equal to 4. So again, if you compute the product 1, 1 times x1, x2, then you realize that AX equal to 4 is exactly this. Okay. How can we write this in MPOL? This is the mod file. Remember, MPOL, you have mod file, data file, and RAM file. Data file is optional. So in this case, yeah, I think in this case, we also use the data file to show you the full example. Everything in MPOL, by the way, that you see with the hashtag is a comment. Okay, so it's not really a command, it's just text that you write to explain what you're doing. So in this case, for example, we define a parameter n that is the number of variables. In this case, we have 2 variables. Why we do that will be clear in a few minutes. We then define a set capital N. This 1 dot n means all the integer numbers 1 to n. So if n is equal to 10, this set will be 1, 2, 3, 4, 5 up to 10. Then we define the parameters C, A, and B. So remember, the parameter C is this 3 minus 2, the values here in the objective function. We define C of n. This expression means that we have C1 and C2. Okay, this is useful later when you see the objective function. And the parameter A, again, is 1, 1. So it's a parameter that includes 2 elements. So this way to write the parameter means that C and A, they have index. I have C1 and C2, and I have A1 and A2. But B is a single number, is the number 4, so I can just define it as parameter B, and that's all, it's a single number. Then we also have variables. As I said, we have x1, x2. So if we write x like that, we are saying that variable x can be indexed by 1 and 2. We have x1, x2, and both of them are greater than or equal to 0. So why is this useful? Why didn't I just write x1 and x2? Because imagine that I have to write 1,000 variables. Now, I cannot write x1, x2, x3, all of them up to x,000. This is much easier. I just define a set 1 to 1,000, and with one line, I have defined 1,000 variables. This is one of the ways MPOL help us define better models in a more efficient way. Now we want to minimize the objective function. Remember, is 3x1 minus 2x2. Okay, so 3 and minus 2 is the parameter C, and x1, x2 are the variable. I can just write like that. What is the meaning of this expression? I'm saying the function I want to minimize is sum j in n. Remember, n is the set 1, 2 of this product. So this translates into C1 times X1 plus C2 times X2. Okay, so again, imagine that you have to write something like that manually for 100 or 1,000 of variables. It will be very, very challenging. But Ample help us with this indexing of the variables, and now we can write even a very long expression with just a few characters. That is very useful. And similarly for the constraint, remember it was x1 plus x2. I mean, this one is not really hard to write, but again, we can use the same syntax. We have the vector A, so this one will be A times x equal to B, and we write it like that. So this is A1 times x1 plus A2 times x2 equal to B, where B is equal to 4, A is equal to 1, and x1, x2 are the two variables. Okay, so this is the way we can write a compact model, but nothing wrong if you want to write with the numbers directly like that, it also works. Okay, so we have a question. Usually you write the objective function first. Frankly speaking, I never try to switch the order. I don't know if it works. It's something interesting to write. But what you need to remember is that you need to define, for example, the variables before using the constraint. This is important. So for example, you may have, like here, you write the constraint. You need to write the variable first. Otherwise, Ample will say, I don't know what you are talking about here. But switching constraint and objective function, I don't know, actually. I never tried. I will, and I will let you know if you want. But yeah, I cannot say for now, but it may work. It may work as well. Okay. Something else about the model. As I say now, set parameter variable must be declared before they are used, and they can appear in any order. The statement ends with semicolons. You can split across line. Remember that upper and lower case is different. If you want to identify an index, like I say x1, x2, you use the square bracket like we did here. And some keyword like sum, in, or subject to, we cannot use them for giving names to variables. What about the data file? Because here you see there are no numbers here. Like we say to Ample, we have a parameter C, A, B, but I'm not telling Ample the numbers or N. So we define that in the data file. So we say the value of parameter N is equal to 2, meaning we have two variables. M equal to 1, I mean, it's just the number of constraints. It's not really useful. You can remove that. Parameter C, the way to define the parameters having like a vector is this. You say the C1 is equal to 3, C2 is equal to -2. So this is the syntax to be used in the data file. Parameter A, A1 is equal to 1, A2 equal to 2, and B is equal to 4. So again, why sometimes we split data and model? Because a model can describe an infinite number of optimization problems, and then we get an instance when we define the data. And if we want to change data because we have to solve multiple instances, it's much easier to have the same model and just iterate through the data file. A run file in this case is model, number of the model. Imagine we call it example.mod. Data is example.dat. .mod and .dat are just for reference, but you can use anything. Actually, it can be even txt. It should work. Option solver simplex. We are telling the solver that we want to use simplex, solve, and then display X. This is the kind of output you will get. So I create a run file. Then I wrote this command, Ample. This symbol means give as input to Ample example.run, that is a run file, and then simplex will tell you the solution. It will tell you The optimal solution is -8, the objective function value, and x1 equal to 0, x2 equal to 4. So if you look at the model, you want to minimize this, subject to x1 plus x2 equal to 4, simplex is telling you the optimal solution is x1 equal to 0, x2 equal to 4, the sum is equal to 4, so the solution is correct, so it's feasible, and both of them are greater than or equal to 0, and the objective function value is 3 times 0 minus 2 times 4 is -8, and this is the minimum you can get. Okay, so when you solve this problem, you have seen, you create the model, you create the data file, you tell Ample with the RAM file what you want to do, and then this is the kind of output that you get. Okay, this is the way you do it on Mac, and I think on Linux as well. On Windows, you may have a different way to solve that. So inside Windows, there is when you download Ample, there is an Ample application in the installation folder. You double click, right? And then there should be a terminal window opening up. And then you write something like that, include the RAM file, in this case, example.run. And then when you click enter, it should work. Okay, yeah, Julia is another software. There are alternatives, yes. One of them is called GAMS, G-A-M-S, is similar to Ample. There are also other software or other packages that you can use. For example, Pyomo is one of them. It works under Python. You can also write directly in C++. There are packages for R. It's really, there are many. The reason why I choose Ample is not because it's the best or the most performing. If you really are interested in having high speed, high efficiency, maybe you need to write directly the code in C++ and call Simplex directly with that. But for the purpose of this course, and in general, when you want to focus on the model rather than the solution, I think Ample is very good because, especially for those without any previous experience in optimization, you can really focus on the modeling without all the other things that comes with, for example, Python or C++, even worse, where you have to deal with many other things on top of this. But Julia, yes, is another one. There are many. I would just say, pick the one that is better for you, that you find more intuitive or easier to use. And there is not really a clear winner. Depends on the application. Usually what I do is for simple proof of concept, or when I have to solve problems quickly, I use Ample. Then if there is something more sophisticated, I may switch to Python or other softwares. But Julia is another one that can be used. Okay, so at this point, we can maybe have an example of a problem here, right? And this is an investing problem. I say that optimization can be used for really in different domains. So here I give you an example that is a little less abstract than the previous one, but I think it's good just to get an idea of what you can do with optimization. So imagine I mean, I hope nobody is from finance here, because they will not like this. It's very simplified, it's not realistic at all. But just for the sake of this application here and this course, imagine that you have two funds, let's call them X and Y, and imagine that you know the return of this fund. So the fund X will give you 4.5% a year, and that you have another fund Y that gives you 5% a year. And then you have $50,000. So what you have to do is to write an optimization problem. Of course, you use Ample and Simplex, as we have seen, where the objective is to find the allocation of the capital to the funds that maximize the profit of the portfolio. Then you may tell me, look, this is, I can tell you directly the solution. Put everything in fund Y. It's giving you 5%. Why should I put something on fund X? So you don't really need to solve the problem at all. You know already the solution. But this is just for the sake of writing the model. Okay, so after this, maybe we can have a few minutes of pause, but let's do this first, because I want to bring you through the process, right? The first thing I told you is we need to understand the problem. So the problem here, I think, is quite clear. Then we need to start to identify the component of the optimization problem. So let's start from the parameters or data. Well, as you know, the parameters, data, is the numbers we know before solving the problem. What are the numbers we know currently? Well, we know the return of the fund X is 4.5%. We know the return of the fund Y, 5%, and we know the total capital, 50,000. So these three numbers represent the data of the problem. Then we also know the objective function. We want to maximize the profit of the portfolio, so the return of the portfolio. What about the variables? Well, the variables, remember, they represent what we will know after solving the problem. And in this case, is how much money we want to allocate to fund X and how much to fund Y. And we also have a constraint. The constraint is that the total amount of money invested is 50,000. There is another constraint, actually, that both the allocation to fund X and Y are not negative. Otherwise, we will be doing short selling. But this is another thing. Let's just keep it simple. These are the components of the problem. I repeat, data, the parameters, what we know before is number one. Number two, the objective function. Number three, the variables. And number four, the constraints. Okay, so these are the four things you need to know in order to describe an optimization problem. At this point, we can write a mod file. So remember, there is mod, dot, and run. Let's start with the mod file. Well, the first thing is to define the parameter and the variables. The parameter is the data. So we know is the return of the fund X, return of the fund Y, and capital. Then we have two variables. We call them X and Y. They are non-negative, and they represent the amount of capital we allocate to fund X and to fund Y. What is the objective function? We want to maximize, I call the objective OBJF, but you can call it return, whatever you want. What is that? Is the total return. Okay, so the return here, in this case, I write 5% as 5, so we divide by 100. But you could also define the return is 0.05, is the same. But let's say we define the return as 5 and 4.5 for the two portfolios. So the total return is Rx, the return of X over 100, times X. X is the amount of capital we allocate to X, plus the return of fund Y over 100 times the amount of capital that we allocate to fund Y. The constraint is that the total allocation to X and Y must be equal to the capital we have. So we also assume that we don't keep cash. We invest everything. So this is the model we have so far. Is it clear? Any question about this model? No? Okay. Okay. So what about data? Well, data, very easy. We have to define the three parameters. So parameter Rx is 4.5, is the return of fund X. Then we have parameter Ry, 5, is the return of fund Y. And then we have the param capital, that is 50,000, the total capital we have. What about the run file? Well, in the run file, we have to define the model, so funds.mod, the data funds.dat. We assume that these two you see here, I call this file funds.mod and funds.dat. And then we have to tell the Ample that we are using Cplex as a software to solve the problem. We tell Ample that we want to solve the problem, and then we want to show the values of X and Y. And if we run that, no surprise, the result is that we allocate everything to fund Y, that is the fund giving us 5% return. nothing to fund 0, and the result is 2,500. That is 5% of this. So this should be no surprise that we get this result. And it's basically what you would expect from this problem. And you see that it was very fast. Usually for solving this is almost immediate. The moment you click, you have the solution. It's also telling you that it did 0 iteration. This dual simplex is just the algorithm that is used by simplex to solve the linear programming problem, but basically found immediately the solution. It was very easy. So this is the solution. Now I think we can have, I don't know, maybe, how much pause do you do here? 10 minutes?
We do this.
Sorry, I could not hear.
15?
15? Okay.
15. Okay.
15 minutes, you say? Because the audio is not really clear. I could not.
Sorry. I'll check at the break. Maybe 15 minutes.
Okay, 15. So we can have 15 minutes. So we can come back at, say, 11:20.
Yeah.
Okay. In the meantime, okay, what I want to, well, this is already done. In the meantime, for you guys, you can start to think at this scenario. Imagine that we have this additional constraint. We cannot invest in fund Y more than twice what we invested in fund X. I want you to think about how you would express this constraint in the model. Okay? So in these 15 minutes, you can also think about that. And when we come back, we can discuss about that. Okay? And we can see, we can come back, yes, around 11:20. In the meantime, if you have questions, you can put in the chat and I will answer later.
Just use solar synthesis. You should activate this license. Just go download and see it work. And those things, but you know, just yeah. Yeah. There is some guidance here, but don't put it up where it should. Put it in. Okay. Seems to work. Something opens.
So next year, this, yeah, I'm going to do it. Yeah, so
Or I'll put some
yeah, maybe.
I was like in the CAB. Oh yeah. Like so because I was like, I mean, like I'm that if I was there, understand where people should be. And this was too easy.
I'll make sure I check it.
At least I could install. Then I forgot just my loss. You know, it's going to be data something. When it's also. Yeah, for example, in Spain, we have the same time as here. And we are like almost one and almost like 15 degrees from the west. Central Europe. Thing is, we live in the civil war, which is that the current German contribution and our neighbors, Portugal, they use they are one. Yes, and United Kingdom too. Even though we have that, we are in Berlin. So, well, we are even on the western United Kingdom, we can interact with but the good thing is that it gets dark later on in Europe. And during the summer, we have light until 9:30, 10 p.m. I mean, that also explains why we have blank on the
Okay, I think we can start again. Anyone got any idea how we can model this constraint? It's basically an additional constraint that we should add to the model to make sure that what we invest in fund Y is no more than twice of what is invested in fund X. So it should be an inequality Okay, well, I will show you. This is how we can write it. Very simple. We add this subject to, I call it fun split, but again, the name is up to you. And we just write that y is less than or equal to twice x. So if we solve the problem now, what will be the solution? Definitely cannot be as before. So the data file is the same, the model file, only the blue line is different, the run file is the same, but the solution now is different. You see that now you are putting 33,333.3 and on fund y and the rest on fund x. So again, you are allocating as much as possible to fund y because this will give you additional like 5% instead of 4.5, but now you have to put something on fund x as well. There is something that I want to highlight here, and is the objective function value. You are maximizing the return, remember, and you see that the objective value now is 2416.67 if we want to approximate. But in the previous case, it was 2500. This is not by chance. In general, in optimization, whenever you put additional constraints on a problem, the objective function can only stay the same or become worse. Because if you think about that, you are cutting potentially some solution that could be optimal, like in this case. So whatever is left cannot be better. Okay, so remember, every time you put additional constraints on a problem, you can only decrease the quality of the objective function, or it stays the same, but it cannot improve. Like in this case, we move from 2500 return to 2416 and so on. Okay, so I just wanted to highlight this, that is interesting if you think about that. Let's move now to the last part of the presentation, that is the max flow problem. Okay. So what is a max flow problem? I don't know how many of you are familiar with that. This is a classical optimization problem, and the idea is that you want to find the maximum flow of goods. It can be anything, it can be oil, electricity, water, whatever, that you can send from a source to a terminal through a network. So this is a network problem. And again, you can have variation of this problem in various fields like infrastructure system. Transportation is a very classical example where you can have flow of cars or anything. But the thing is that this kind of problem is very simple in its basic definition, but then variation of that can really be applied to many real world problems. What do I mean by it's a network problem? It means that the basic structure we are working with is a network, and this is a network. A network is a collection of nodes and arcs. So the circles are nodes, and then you have arcs that are connecting different nodes. For example, node 4 and node 5 are connected through an arc. It means that I can send something from 4 to 5. In this case, arcs have orientation. It means I can send from 4 to 5, but I cannot send from 5 to 4. These are called arcs. Other network problems that you can find where instead of arcs you have edges. What is the difference? The difference is that there is no orientation. So an edge will be just a link between two arcs. You have no arrow. It means you can send from 4 to 5, but also 5 to 4. But in this case, we have orientation. So the basic structure we are working here with is an oriented graph or network. And again, the meaning is that whenever a link connects a node with another one, A to B, means you can send something from A to B. That's the idea. You see here there are two special nodes, the red one and the green one. The red one, the node by S, is the source. It means that we start to send our goods from the red node, and we want to reach the green one, that is the terminal. So the idea is that if you go back here, we want to find the maximum flow of goods that can be sent from a source to a terminal. It means we are sending our goods from the node 6. Imagine we can send as much as possible. There is no limitation. And we want to reach the green node, moving through this network. Let's use Ample to define a model representing the situation I just mentioned. Again, in Ample, if you remember, we need to define objective, constraint, variables, and parameters, and sets that is not really part of the optimization problem, but is mostly what we use in Ample to index the variables to make easier the writing everything else, the constraint and the objective. So what are the sets that we have here? Let's say we have a set V that is a set of vertices. That means these circles. And then we have a set A that is the set of arcs. And an arc can be identified by a pair of vertices. So an arc ij is the link that connects node I to node j. Then we have variables that are the flow through each arc. In other words, how much material is flowing through each one of these arcs. Then we have the parameters. Number one is the capacity, because you can imagine that through each arc, we can only send up to a certain amount of quantity. For example, we can say if we are sending water, that each arc can only, let's say, I don't know, if 4 to T, we can send no more than 4 units of water, or it can be electricity, but we need to have some capacity. Because if we don't have capacity, we can send basically any amount. So in this case, imagine that each arc is characterized by this parameter called capacity, telling us the maximum amount of material, good, whatever it is, that can flow through that arc. Then we have a parameter n that is a number of vertices. And then we have two parameters, s and t, that are the indices of the source and terminal vertex. In this case, the source here is the node 6 and the terminal is node 7. What is the objective function in this case? We want to maximize the total flow. So in this case, I mean, the constraint will tell us later what I just mentioned now, but we cannot create material from nowhere. Whatever enters from node 6 must reach node 7. In other words, there is a conservation of the flow. So if we want to maximize the total flow, how can we characterize that? Well, it can be the total amount of flow that is flowing out from node 6, or in a similar way, is the total amount of flow that is entering the node 7. Because if nothing is created from nowhere, everything that comes in will be reaching the terminal. So the objective function, the total amount of flow that we want to maximize, is the total amount of flow going out from node 6, or the total amount of flow entering node 7 is the same. So in this case, we are maximizing the total flow that is going out from the source. You see, we are summing is the sum of the flow Sj, where S is the source. So we are summing the flow going out from S, S4, S3, S9. What is the set of constraints? The number one is that we cannot send through each arc a flow that is exceeding the capacity. And the second one is the flow conservation. Is basically representing the concept I just highlighted, that the flow cannot be generated from nowhere. For every node that is not the source or the terminal, the sum of the flow entering the node must be equal to the sum of the flow going out from the node. So in other words, take node 4 for example, it means that the flow that is entering node 4 from S, so through this arc, must be equal to the flow that is going out from node 4, so the sum of the flow going to node 1, 5, and 7. And this for each node that is not the source or the terminal. So this is called flow conservation sometimes. Okay, and the way to write it in Ample is this. You see, for each node I, this is ij, so is the flow going out, and the sum over ki is the from k to I, so entering node I. So here we are saying whatever is going in must be going out for each node that is not source or terminal. How can we write this in Ample? So let's start again, as usual, from the mod file. We define the parameters, the number of nodes, the source and the terminal node, the set of vertices, the set of arcs. This within is a new keyword. It means that you take the set of all the pairs, all the combination of vertex, and the set A is a subset of this. Okay, but this set A, V, everything else will be defined in the data file, because every arc is defined by a pair of vertices, as we say. Then we have a capacity A. For each arc, we have a capacity that is the maximum that we can send. And in this case, just to make it simple, let's assume that all of them have capacity 10. Okay. But of course, these numbers may be different for each arc in a realistic application. Then we have the variable that is the flow, and the flow is defined for each arc A. The flow is non-negative. Objective function, we want to maximize, the objective here is called total flow. And as I said, we can define it as the flow going out from the source or the flow entering the terminal. In this case, is the flow going out from the source. Capacity bound is the fact that for each arc, we cannot send an amount of flow exceeding the capacity. And then the flow conservation is what I said earlier. This symbol here, small, greater, means different. So what I wrote here, I different from S and T, we can write like that. I, small, greater means different from S, and I different from T. So this is the model. And then we have the data file. So what do we do in the data file? We need to define that the source is vertex 6, the terminal is vertex 7, and n equal to 9 means that we have 9 vertices in this network. See, from 1 to 9. So here we define these values, and then we have to define the set A. So the way to define set A, because we wrote here that is a subset of VV, it means that each element of A must be characterized by an element of V followed by an element of V. And V is what? V is the set of vertices, so 1 to 9, the index of the vertices. So every element of A here is a pair of numbers defining the two vertices from 2 where the arc is lying. So for example, 1, 2 means that I have an arc connecting node 1 and node 2. Each arc is identified by the starting and ending node. And if you look at this list, you should have all the arcs that are in the picture, because this picture is representing exactly the problem that I'm modeling in Ample. So this is something else that I think is quite interesting, how you take a problem that is defined visually like that, and how you can mathematically express what you see on the screen this way. Finally, we have the run file. So as usual, we say that the model is maxflow.mod, data maxflow.dat. Option solver simplex means that we want to use simplex to solve the problem. Solve means we want to solve the problem. we display f. F is the flow, so the variables. When you have a set of variables indexed by a, in this case, or something, you just need to write the name of the variable f, and Simplex will tell you the list of the values. And then when you have this run file, you save the run file, and then if you are on Mac, this is the way to run. If you are on Windows, there was the slide earlier telling you what you have to do. You have to double click on the Ample application in the download folder, and then you have to write include maxflow.run. You click and it should run. This is more or less the idea. So what happens if we run this file? What will be the optimal solution? Well, the optimal solution will be the one where you send as much flow from the red node to the green node. So let's see how it will look like. This is the output of Simplex. So Simplex will tell you for each arc, the flow going through the arc, and then you see also in blue here, the objective function value. The objective function value 30 means that from the red node, you have 30 whatever unit, whatever it is, but you have 30 units flowing out from the source node that is also equal to 30 units entering the terminal. And here you will see the values for each arc, how much goods are flowing. So for example, there is nothing on arc 1, 2, nothing on 2, 3. There are 10 units on 3, 7. So you see this is the output that you would see if you run this with Simplex and Ample. Now, if you remember at the beginning of the lecture, I say that it's also important to translate back the solution into the original problem. So let's have a look at the meaning of these numbers. What I did here, I highlighted the arcs where we have 10 units of flow going, and the arcs that are, as before, they are associated with zero flow in the optimal solution. So what is the meaning of this solution? It means that, remember, in this example, every arc has a capacity of 10 units. Okay, it's just to simplify. It means that from the red node to node number 9, I have 10 units. Then red to 3, I have 10. And red to 4, I have 10. Then node 9 to the terminal, I have 10 units. Node 3 to the terminal, I have other 10 units. And node 4 to the terminal, I have other 10. In other words, you have 10 units going from S to 4 and then reaching the terminal. 10 units going to 3 and then reaching the terminal, and 10 units going to 9 and reaching the terminal, for a total of 30. So it's correct that Simplex is telling us that the objective function is 30. The max flow, the amount of flow going from the red to the green node is 30. And here you see how this flow is flowing. Is there any questions so far on this problem? Because this will be the problem that we will be using next lecture as a basic problem. So it's important that it's clear. What is the idea? What is the objective? What are the components of the problem? How this works? If you have any question, just let me know in the chat. But this is more or less the idea. And you can imagine, because we are speaking about resilience, and we will be introducing disruptions later, that if now I destroy one of these links, I cannot achieve the flow that I have here. So I may have to choose alternative route to reach my terminal. And there are interesting questions like, if I don't know in advance which kind of links are destroyed, what can I do? Or for example, can I make some of the links indestructible in order to guarantee that I have the best possible flow? If I have limited resources, maybe I can only protect 1 or 2 links. Which links should I protect so that in the worst case, the disruption, in the worst case disruption means I don't know what the disruption will be, but assume it will be the worst, what should I protect in order to make my flow as good as possible? This is where the concept of resilience will be introduced and the robust optimization, but this will be the topic of the next lecture. For now, what is important is that you understand that the flow model we introduced, the components, the arcs, and the nodes, how these ample work, and how to interpret this solution visually like that. So what is the summary here for today? We have learned a lot of things. We have learned the basic of mathematical programming. So we have learned that mathematical programming allow us to describe problems, optimization problems with where the components are the parameters, the data, right? The constraints, the objective function, and the variables. We can model that first on the paper, and then if we want to solve the problem, we use software like Ample to create the model, not to solve, very important, to create the model, and then we need solver like Cplex to solve the problem. We have also learned what is the max flow problem, and now we can model and solve this problem using Ample and Cplex, because what you see here is what you find, what you get when you run your run file, and then you have Cplex telling you that this is the solution. So this is what we have learned in this today in this lecture, and the next lecture, as I already mentioned, we will be looking at what happens when arcs of the network can be destroyed. In some situation, it can be random disruption, but in this case, we are looking at worst case disruption. Worst case disruption means, for example, you have an enemy, an attacker, a terrorist, whatever, that is destroying your system with the aim to decrease the flow as much as possible. So it's a kind of game theoretic framework where there are two players. You are the defender or the person that want to send as much flow as possible, and then you have an enemy with the objective that is opposite of yours. He wants to decrease the flow, and to do that, he can destroy links of the network, and you can do something. You can, of course, after the disruption, you can send the flow that the best way you can, but you can also fortify the system before the disruption takes place. Of course, the challenge here is that you don't know the disruption. So you need to really carefully choose how you allocate your fortification resources, or in other words, which links of the network you want to fortify if you want to make the life harder to the enemy. But again, you don't know what enemy will do, because the enemy can destroy the arcs and you have no idea what he will do. You only know that he will do the best he can to minimize the flow you can send through the network. So the resilience concept in that case will be defined based on this framework, and I think it will be a different concept of resilience compared to what you have seen so far, because resilience is something, I guess you have realized by now, that depending on the application can be defined in different ways. For some people, resilience is the time to recovery. For some people, can be the area under the curve of the recovery function. In this case, we are looking at resilience in a different way. And the resilience, we will see this in the next lecture, but just for you to know, will be associated with the amount of resources that the enemy needs to destroy our network. Or if you want to look at it from the game theory point of view, the amount of resources that the enemy needs to win the game. So it's not really about the time to recovery or other metrics. It's really about making it as expensive as possible for an enemy to destroy our system. This is the way we measure the resilience in this application, because we can assume that a system is more resilient if enemy needs more resources to destroy the system. Hopefully, the amount of resources he got will not be enough to do that. But since we don't know, this information is often private. We don't know how much resources the enemy got. The best we can do is to make him pay as much as possible. This is more or less the idea, but again, this will be later. What you have to do before the next lecture. First thing is, if you have not yet downloaded Ample, you can download it here and install the demo version. The demo version is fine because the size of the problem we are dealing with is not huge, so you don't need the full license that is not free. The demo version should come with the software Cplex. Okay, so when you download this here, inside you should have also Cplex. I think you should have received, or you will receive soon, a very small example. I call it x.run, right? And this is just to check that your Cplex and Ample are working fine. So what you do, you download your Ample, you decompress the folder somewhere, you put your x.run inside, and you try to run it. And you should get the solution. If you get any error, you let me know. Remember, all the files that will be shared with you must be in the same folder where there is the Ample and Cplex, right? So when you decompress, put them inside. Otherwise, you will not find the solver and the other source file. And remember the other thing, if you are under Windows, so if you are under Mac, the way to run is this: Ample, then the symbol of less, and then the name of the run file. If you are under Windows, you need to do this. Let me find, yeah. If you are under Windows, what you need to do, you double click the Ample application. When you decompress Ample, there will be the Ample executable file. You double click, then you will have a small terminal, and then you write include, and then the name of the run file, and you click enter. So instead of writing Ample, this symbol, and run file, on Windows, you should write include this, and then you click. Okay, so this is the main difference, but it should work. We tested before. And also, if you want, you can have a look at there was the link in the slide that will be also shared with you of the guide, Ample guide, if you want to learn more. But what you've seen so far is enough. Also, there will be other files shared with you. Do the same as the run file, decompress everything in the same folder, because in the next lecture, we will have some kind of interactive activities. So during the presentation, I may ask you to do something with the file that I share with you, and then you run your code, and then you get the results. That's why it's very important that Ample and Cplex are running before the next lecture. If you have any problem, any question, anything that is not clear, or maybe with the installation or something about the content, you can write me to this email. And maybe these last, I don't know, 10 minutes or so, if you have any question about the content of today, something was not clear, I can answer to the questions you have.
Okay, thank you. So maybe I can quickly please share my screen to show you
Yes.
here's where I put the information. So all that you need is now Moodle. I'm sorry, you were not there before. So now here you have the link to download RNPL, and so don't use the candidate full trial, or you should have registered the trial. I think the size limited demo.
Yeah. That one should be fine, the size limited demo.
Yeah, so you have just a folder that you put wherever you want, so let's see which you put all the modern run files for the examples. So here you have the example watch file, example run file, which you can download also, which you put in your Ample folder. So that should be working for you. There's a bit more instructions here. Yeah, so if you need help, just ask, and that's all. But normally all the instructions are on the should work.
Yes.
Okay.
And I see there is a question in the chat from Dominic. So how does this approach solve the max flow compared to the 4 Fulkerson? Okay, Ford-Fulkerson is another algorithm to solve the max flow. The reason why we use here the mathematical programming model that I share is because this will be the basic component to create in the next lecture, the other, how to say, to introduce the resilience. Because to introduce the resilience, we will have to find the best way to fortify the network. And to find that as a sub problem, we have to solve in a way the max flow that you have seen, actually the dual. So this it will be clear the next lecture, but let's just say that Ford-Fulkerson is like a methodology you can use to solve the problem. I remember when I studied OR in the final exam, they asked us to solve something like that by hand with the Ford-Fulkerson. And I mean, in practice, it depends on the size of the problem as well. In this course, the reason why we choose to use the LP approach that you have seen is because we need something called duality, that again will come in the next lecture, in order to find the best way to protect the network against attacks. So this is the main reason. But yeah, Ford-Fulkerson is another algorithm that you can use to solve the problem. In many problems in optimization, actually, you can use the way that I described to you. So write the mathematical programming problem and then solve with a commercial general purpose software like Cplex, or you can design specific algorithms that are just tailored to the problem that you are solving, like Ford-Fulkerson, but there are others. The idea again is that my approach usually is, if there is a problem for which an algorithm is already there and is efficient, you may use that one. But if it's a new problem, a new optimization problem, usually the first approach I suggest is to try to solve it with the general purpose software, because it will be faster in terms of writing the model and running. If you cannot solve, then you can think about specific algorithms that are doing something smarter, or maybe using heuristics. But my first choice is always to go with this one, because if you can already solve this way, then it's good enough. If you cannot, because the size is too big, then you may need to resort to some kind of specific approaches, ad hoc algorithms, heuristic, and so on. So that's my suggestion in like when you have to choose between LP or specific algorithms. If the algorithm already exists, fine. But if you have to model a problem that is new and some real world problem may not even be close to problems that are already studied in the literature, then I think it's more efficient to go with the LP mathematical programming approach first. And only if that fails, you can go to more time-consuming approaches, time-consuming in terms of the time you need to find the algorithm to solve the problem or to implement the specific approach that you need to use. I don't know if this answered your question. Okay. Any other question?
Okay, for us here in the room, I think everything's fine.
Okay.
Yeah, I think we can leave here. Thank you very much.
Thank you, and thank you to everyone who attended. I think is again maybe a different way to look at resilience, but I really hope that you also learn a little how to use MPOL, and you may even use it in other occasions, because having a basic knowledge of how to solve in practice with some software optimization problems, I think is a very useful skill. So I hope that on top of resilience, this will be a byproduct, if you want, of this course, that you learn how to solve some easy optimization problem in practice.
And let's close the session and see you next week. And it doesn't follow us in the
Yep. Thank you. See you next time.
The 30-day free trial. That's where you need the reference. So again, about this one, you want that one, because I will be able to. And that, it's different from your.
Yeah. Oh, no.